Chapter 8, exercises 9, 10, and 11 all ask you to use the molar volume to calculate each of the following things at STP. First thing I want to unpack here is what STP is. So STP stands for Standard Temperature and Pressure. So scientists are working in lots of different laboratories all across the world, and so they come up with standards that they can all reference their work to or perform their work at so that they can compare their results with each other, so that ultimately they work as a team. And so internationally, scientists have chosen a standard temperature and pressure at which to work. And at this standard temperature and pressure, different materials have dependable properties. So the standard temperature that people chose was 0 degrees Celsius, and the standard pressure is 1 atmosphere. 0 degrees Celsius is the temperature at which water freezes and becomes ice, and 1 atmosphere is the amount of pressure exerted by the atmosphere, the Earth's atmosphere, on a person standing at sea level. So those are the standards for temperature and pressure. And what's unique is at that standard pressure and temperature, 1 mole of any gas takes up 22.4 liters. 1 mole of any gas at standard temperature and pressure takes up 22.4 liters. That's around 6 basketballs of space. Okay, so notice that that's a conversion factor that we can use to get from moles to liters or liters to moles. So that's the new part of these problems. Everything else are things we've seen before. Okay, so let's dive right in. A says we're looking for the number of moles. So we're looking for the number of moles of O2. That's what we want. And what the number that they're giving us is 44.8 liters of O2. 44.8 liters of O2. So we need to know how these units relate. How do liters of O2 relate to moles of O2? And because this is being done at STP, all of these questions will be done at STP. Because of that, we can use this conversion factor at the top. 1 mole of any gas. 1 mole of any gas will be equal to 22.4 liters of that gas. So these numbers are coming down to give you the numbers in this conversion factor. All right, well, once we have the conversion factor, we can take the number they give us. Every time you do a conversion, write a multiplication sign, a fraction bar, and the units that you start with on top, so here that's liters of O2, those are going to be the units you want at the bottom of your fraction so that those units will cancel out and change to the units you want. So we're going to take the part of the conversion factor that has liters of O2 and put that on the bottom of the fraction. Going over the fraction bars like going across the equal sign, so on top we'll have 1 mole of O2. Liters of O2 will cancel out because one is on the top of the fraction, the other's on the bottom. And we're going to be left with moles of O2, which is exactly what we want. So you just want to plug this into a calculator. So you do 44.8 times 1, enter, divided by 22.4, enter. And what you should get is 2 moles. So 2 moles of O2. That's the number of moles of O2 in 44.8 liters of that gas at standard temperature and pressure, STP. Okay, let's try B. So they want the volume in liters. They want to know how many liters of this gas are occupied by, and here's our number, 0.42 moles of helium gas. So we have 0.42 moles of helium gas. And remember that MOL is the abbreviation for MOLE. So you could write either one. Okay, so this is really a conversion. We need to get from moles of helium to liters. In order to do any conversion, you need a conversion factor that relates the two units. So how do moles of helium relate to liters? Well, because this is happening at standard temperature and pressure, we can use this purple conversion factor in the top. At standard temperature and pressure, 1 mole of any gas takes up 22.4 liters. So that's our conversion. All right, once we have our conversion factor, we can take the number they give us. Every time you do a conversion, write a multiplication sign, a fraction bar, and the units that you start with on top, here those are moles of HE, those units will always go on the bottom because you want those units to cancel out and change to your answer, the units of your answer. So we want moles of helium on the bottom. So we take the side of the conversion factor that has moles of helium and we put that on the bottom. Going over the fraction bars, like going across the equal sign, so on top we'll have 22.4 liters. Moles of helium will cancel out because that one that I just crossed out is sort of on the top of a fraction, and this one that I just crossed out is at the bottom. And we will be left with, liters, which is exactly what we wanted. That's that unit that we're left with on top. All right, so we just have to plug that into a calculator. So we take 0.42 times the top times 22.4, enter, divided by 1, enter, and you should get 9.408. So 9.408 liters, that's the number of liters that would be occupied by 0.42 moles of helium gas at STP. All right, let's take that same procedure and we're going to go to question 10. So in question 10, they are asking us for the volume in liters, so that's what we want, occupied by, and here's the number they give us, 2.5 moles of N2 gas. So 2.5 moles of N2 gas. All right, so it's a conversion problem. In order to do any conversion, you need a conversion factor that relates the two units. So how do moles of N2 relate to liters? Because this is happening at STP, we can take this conversion factor that we saw above, and I'll write it down here again just for reference. We know that because this is happening at STP, that 1 mole of nitrogen gas will take up 22.4 liters. That conversion factor can always be used at STP. All right, so now we have our conversion factor. We can take the number they give us. Every time you do a conversion, write a multiplication sign, a fraction bar, and the units that you start with, here moles of nitrogen, are always the units you want to go on the bottom of the fraction so that they cancel out. So here we want moles of nitrogen on the bottom of the fraction. So we take the side of the conversion factor that has moles of nitrogen, put it there. Going over the fraction bar is like going across the equal sign, so on top we're going to have 22.4 liters. So moles of nitrogen will cancel out. We will be left with liters, which is exactly what we wanted. And we just have to plug it into a calculator. So 2.5 times 22.4, enter, divided by 1, enter, and you should get 56 liters. It's quite a lot, 56 liters, a lot of space. So that's how much space 2.5 moles of nitrogen gas would take up at STP. All right, B. They're asking for the number of moles of CO2. So we want moles of CO2, carbon dioxide. And what they give us, here's the number, is 4 liters of carbon dioxide. So we have 4 liters. So this is a conversion. And in order to do any conversion, we need a conversion factor that relates the two units. So how do liters relate to moles here of carbon dioxide? Because this is happening at STP, we can use this conversion factor, but that relates moles to liters. So for every 22.4 liters at STP, you'll have 1 mole of any gas. Okay, now that we have the conversion, we can take the number they gave us. Every time you do a conversion, write a multiplication sign, a fraction bar, and the units that you start with on top always have to go at the bottom so that they'll cancel out and turn into the units you want. So we want liters on the bottom. So we take the side of the conversion factor that has liters and put that number on the bottom. Going over the fraction bar is like going across the equal sign. So on the top, we'll have 1 mole of CO2. Liters will cancel. This first liter is on the top of a fraction, the second one's on the bottom, so those cancel, and we are left with moles of CO2, which is exactly what we wanted. So now we just plug this into a calculator. So this is 4 times 1, enter, divided by 22.4, enter, and you should get something like 0.179 moles. I'm getting 0.17857, etc. But you can round the 5 up, and you'll get 0.179. And so that would be the number of moles you'd have in 4 liters of carbon dioxide at STP. Okay, let's bring this conversion factor, which has been so useful, down. We'll copy this and bring it down to question 11. So question 11 is pretty much the same thing we've been doing, except there's going to be one more step. All right, so we're still dealing with STP. Everything's going to be at STP, so we can still use this conversion factor. The question says, find the volume in liters, so that's what we're looking for, taken up by, and here's the number, 6.4 grams of O2. Okay, well, we know that this is happening at STP, and so we'll know that in every 1 mole of O2, we'll have 22.4 liters. That's a conversion factor that we get and that we think of just because we saw the words STP. And so that would let us get from moles to liters, but we don't have moles, we have grams. So we have to get from grams to moles, and we saw that in previous chapters, chapter 7, that you can get from grams to moles using the molar mass. So if you look at, so we have only oxygen in this compound. We have 2 oxygens, and if you look at the box on the periodic table, underneath oxygen should be the number 16. So 1 mole of each oxygen will weigh 16 grams. We have 2 moles, so together they'll weigh 32 grams. So there are going to be 32 grams of oxygen in 1 mole of oxygen gas, O2. So what you do is you take the number of the element you have and you multiply it by the number at the bottom of the box on the periodic table for that element. And then you add those up and you get the number of grams in 1 mole of that compound. Okay, we'll do this again in part B, so you'll get to see it in another example. So we can use this first conversion factor to get from grams to moles, and the second conversion factor to get from moles to liters, and that's what we want. So we have all the conversion factors we need. We can take the number they gave us. Every time you do a conversion, write a multiplication sign, a fraction bar, and the units that you start with on top are you want to put at the bottom so that they'll cancel out. So we want grams of O2 to be at the bottom there. The only place we have grams of O2 in our conversion factors is in this first one, so we'll put grams of O2 there. Going over the fraction bars, like going across the equal sign, so on top, we'll want to put 1 mole of O2. Notice how grams of O2 cancel out. And if we were to stop right now, we would be left with moles of O2. But we don't want moles of O2, we want liters. So we have to do another conversion. Every time you do a conversion, write a multiplication sign and a fraction bar. The units that you start with on top are the ones that you want to put on the bottom of the next fraction so that it cancels out. So here, that's going to be moles of O2. So we take the side of the conversion factor that has moles of O2 and put that on the bottom, going over the fraction bars like going across the equal sign, so on top we'll have 22.4 liters. And you can see how moles of O2 will cancel. So we're going to be left with liters, which is exactly what we wanted. And now we just have to plug this into a calculator. So the way you do that is you take 6.4 times 1, enter, divide by 32, enter, times 22.4, enter, divided by 1, enter, and you should get 4.48. So if you weighed out 6.4 grams of O2 gas, at STP that would take up 4.48 liters. Okay, let's try that same procedure again with B. In the case of B, they're asking for the number of grams of H2. And what they give you, the number they give you, is 1,620 milliliters of H2 gas. Okay, now the one key thing that you don't want to forget is that in this problem is happening at STP. And because it's happening at STP, we know whatever else happens, that 22.4 liters of this compound will be 1 mole of this compound. All right, well, we don't have liters and we don't have moles, but we have things that we can relate these to. For example, we have milliliters. And we would know from the very first chapter that there are 1,000 milliliters in 1 liter. So we can use this gray conversion factor to get from milliliters to liters. We can use the purple one to get from liters to moles. Then we just have to get to grams. And we can get from moles to grams using the molar masses on the periodic table. So you would want to add those up. Now, the assumption you make is that you have 1 mole of H2, and you want to know how many grams of H2 that's going to be. So, list each of the elements in your compound. Here we only have hydrogen. We do have 2 hydrogens, though, so I'm going to put a 2 here. If you look at the box on the periodic table and hydrogen's in the top left, you'll notice that there's a 1 at the bottom. It's the 1 at the bottom that tells you how many grams are in 1 mole. So each mole of hydrogen will weigh 1 gram. Because we have 2 moles, it'll weigh 2 times 1, or 2 grams. So 1 mole of H2 gas will weigh 2 grams. And so we have our last conversion factor. Oops. The one that lets us get from moles of H2 to grams of H2. All right. Once you have your conversion factors, you can take the number they give you, so 1,620 milliliters. Every time you do a conversion, write a multiplication sign, a fraction bar, and the units that you start with on top, you'll want to put on the bottom so that they'll cancel out. So here, that's milliliters. So you'll take the side of the conversion factor that has milliliters. This is the only conversion factor that has milliliters, the gray one. You'll take those milliliters and you'll put them on the bottom of this fraction. Going over the fraction bar is like going across the equal sign, and so on top, we'll put 1 liter. Milliliters will cancel out, and we'll be left with liters. But we don't want liters, we want grams of hydrogen, so we get to do another conversion. Every time you do a conversion, write a multiplication sign and a fraction bar. And the units that you start with on top, you want to put on the bottom so that they'll cancel out. So here, that's liters. So we'll go to our next conversion factor. And we take the side that has liters and put that on the bottom. Going over the fraction bar is like going across the equal sign, so on top, we'll have 1 mole of H2. This 1 mole of H2. Okay, notice how liters cancel out, and we're left with moles of H2. But we don't want moles of H2, we want grams of H2, so we get to do one more conversion. Every time you do a conversion, write a multiplication sign, fraction bar, and the units that you start with on top go on the bottom of the next fraction so that they'll cancel out. So here, that's moles of H2. So we'll take the side of the conversion factor that has moles of H2 and put that on the bottom of this fraction. Going over the fraction bar is like going across the equal sign. So on top, we'll have 2 grams of H2. Notice how moles of H2 cancel, and we're left with grams of H2, which is exactly what we wanted. So we're left with grams of H2, and all we have to do is plug this into a calculator. So the way you do that is 1,620 times 1, enter, divided by 1,000, enter, times the purple 1, so 1, enter, divided by the purple 22.4, enter, times 2, that's in orange, enter, divided by 1, enter, and you should get 0.1446 grams of H2 gas. Okay, so that's how many grams of H2 gas, that's how much 1,620 milliliters of H2 gas would weigh at STP, standard temperature and pressure, 0 degrees Celsius, 1 atmosphere. So notice in these problems, we started out relating moles to liters at STP. That was the heart of the problems. And the only way that these last two became a little more difficult was they gave us grams instead of moles, so we had to convert from grams to moles using the molar masses, or they gave us milliliters instead of liters, in which case we just converted to liters using the metric conversion factor that we learned so long ago. So ultimately, the new thing with these problems is using STP to relate the moles of a gas and the volume of a gas.